Okay, today we are together for HDR defense of Michael Bulois. Michael, you have 1 hour to present your work, and this presentation will be followed by questions, discussion with jury members.
Okay, thank you very much, Nicola. So I'm very glad to present you this habilitation talk, and I would like to thank all the jury members for being here today, and especially the referees for writing a report on my works. So it's about commuting varieties and some related varieties, let's say. I will divide the talk in three parts. The first part is about commuting varieties and some other settings around it. And I will speak on two particular works I've done about sheets first and then about Hilbert schemes. So first, the name of the game, the commuting variety. So the commuting variety is a set of pairs such that the bracket of x and y is 0. And I should precise here what is G. G is a reductive Lie algebra. And the most common example, the standard example, is G is the set of n times n matrices, square matrices, and where the bracket is just x times y minus y times x. And these Lie algebras are the Lie algebras of some algebraic groups. For instance, here G is just the Lie algebra. We write it as GLN, the Lie algebra of the general linear group. Okay, and I will work mostly over C, even if most of the thing works over any algebraically closed field of characteristic 0. Another example is when G is a special orthogonal group and the Lie algebra is written small son, and this is the set of antisymmetric matrices. So we have this group here, big G, and G acts on small g with the adjoint action. In the case of matrices, this is only the conjugation by an invertible matrix. And the commuting variety is a G variety. It acts by simultaneous action on each part. Okay, so this is one fundamental thing, and I will zoom out a bit to show you some other settings. So this is the setting of reductive Lie algebras. And one possible generalization is to consider Z2 grading on a Lie algebra. And then this is what is called a symmetric Lie algebra. What we ask in this Z2 grading is that Gi, Gj is included in Gi plus j. And there, G0 is a reductive Lie algebra associated to a reductive group, and we have G0 acting on G1. One example is the action of SON, special orthogonal group acting on the set of symmetric matrices. So this is the case of polar decomposition. You see that G is just a decomposition into antisymmetric and symmetric matrices. What you can consider is, again, the commuting variety, and you look at the commuting variety in G1, the set, let's say the set of pairs of symmetric matrices, and this is a G0 variety. Okay, one more step of generalization, one intermediate step first. You can think of Weinberg theta groups, where basically you replace the 2 in the Z2 grading by an M arbitrary. I will not speak much about it. And one more step of generalization is to consider a representation. So here H is an algebraic group, and V is just a vector space equipped with a linear action of H. Then you can consider C of V as the set of X phi, which lives in v times v dual, and we ask that phi vanishes on the tangent space of the action of h at x. And this is a special case of zero fiber of a moment map. So here you have a moment map mu, which goes from v times v dual to h dual, and what I say is that c of v is mu minus 1 of 0. And all the settings I presented above, let's say c of g1 or c of g, there are special cases of this thing. So here the keyword is symplectic geometry. Okay, other related varieties to this setting are the following. You can consider also the nilpotent commuting variety, where you ask only the element to be nilpotent. And one other direction of generalization is to consider non-reductive Lie algebras. And one example that's of interest for me is the case of A equal to a parabolic subalgebra. With the canonical example in GLN, then P is just a set of endomorphism which stabilize a flag, a given flag. So in some basis, this can be written as an upper triangular block matrices. And you can consider the commuting variety of P. Okay, so that's one step further, and I will zoom out a bit to tell you where are the objects of this talk. Okay, so this is the same picture as before, and what I want to do is to tell you where my works fit in there. So this is the list of the works I presented for the habilitation. No matter if you can't see it clearly, but there are several questions, and for instance, what I looked with my co-authors Ronan Terpereau, Manfred Len, and Christian Len. So this is what is written BLLT 17, and also something related that I did alone was about this symplectic setting where we looked at symplectic quotients, and this is very related to this variety C of V, and it was in the polar case. Maybe I can change color here. Okay, one of our works was about the commuting varieties in the symmetrically algebra setting. So this is BU11B, where I looked at the irreducible components of this variety. Also, during my PhD, I looked at the nilpotent commuting variety of a symmetrically algebra. One other important thing here is the nilpotent commuting variety of a given parabolic in type A, so in JLN. And this was related to the Hilbert scheme, which I will introduce later. So nested Hilbert scheme, let's say. So first I wrote a paper with Laurent Evin, and then we pushed the study further with Magdalena Bus. And one thing that does not appear here is the sheets, which are related to the commuting variety in a way I will present soon. And this is the last paper with Pascal Hiver, plus some PhD result. And what are the questions we are studying about the commuting variety? First, there is the question of the structure of this variety. Let's say set theoretically or some easy geometry. So we can ask for the dimension of this variety involved. We can ask on the irreducible components, whether the variety is irreducible or not, or what are the irreducible components. We can look at finer geometry problem. So I have in mind smoothness or smooth locus, also normality question, and also reducedness question. And also there is all the question of invariant theory. So this is about quotients. by the action of G, quotient, classical invariant theory, geometric invariant theory. And what I will speak about in this talk is about two things. This thing here, about sheets, and about the Hilbert scheme and the link with the commuting variety. Okay, so that's for the setting. There are many things here. But we have not discussed yet about really this variety. What does it look like? What can we say about this variety? And it's quite an involved variety. It's not really easy to have a full understanding of this variety. It's a singular variety, but we don't really know what does the singularity looks like. Is that like a normal cone? We don't know really the types of the singularity here. What we know is the dimension. It's not hard to see that the dimension of the variety is the dimension of G plus the rank of G. This means that in the easiest case, where G is just the SL2, the traceless matrices of size 2, we have the dimension of G, which is a 4-dimensional variety, which lies inside a 6-dimensional space. So this is not really easy to draw a picture of this thing. But there are some conjecture which states that it should be a normal variety and it should be reduced. That is, the equation defining this variety are the only equation are generating the ideal of vanishing polynomials on this variety. So that is to say that there are some complicated questions on it, and I'm going to show you the easy part of the commuting variety. What's the easy part? We do as physicists do. When we have a problem, we look for the linearity. And where is the linearity here? If you fix an element x here, you can look at all the elements commuting with S. So this is what I written Gx. So this is the set of Z such that x, Z is 0. This is not really surprising. But what is important here is that we have a vector space. This is the kernel of a linear map. And so we have something in the commuting variety which is this xgx. So the fibers under the first projection are linear space. What you can do then is to look at the orbit of such a thing, or the orbits. And this still lies in the commuting variety, and here you get something which is much bigger. You can compute the dimension of this thing. This is of dimension, the dimension of the Lie algebra. And this is for any x. When I speak with numericians, they always ask me, why do I want to look at all the different Jordan normal form of an element? Why don't you approximate and approach it by, let's say, diagonalizable matrices? And this is the reason. Here, any element, even 0, contributes with the same dimension in the commuting variety. Now, there is one case where this remark is important. If the number of g-orbits, here it's not possible in this setting, but in some other related setting it's possible. If there is only finitely many g-orbits, then you can write C of G as the disjoint union of gx here. And this is a union on the different orbits. And here you have a finite union, so you know that your variety is of dimension G, and this gives you a decomposition into irreducible components. But it's not the case for Lie algebra, but just an analogy which arises in some other setting, like in the nilpotent commuting variety, where you have only finitely many number of nilpotent orbits. This writing is quite rough. We can do better. Here we can consider all the elements which have the gx as centralizer. So here the reg is to say that the dimension of gz, we have some z here, if only if the dimension of the centralizer for z is the same as the dimension of the centralizer for x. And this is also equivalent to equality of orbits. And again, what you can do is take the g orbit of the action of g on all these things, and you have something important which arises here. This is this. Such varieties are only finitely many. They are what are called decomposition classes. I will speak of it a bit later. There are finitely many, so C of G, once again, can be written as a disjoint union over, let's say, J of these things. So and you can compute, for instance, the dimension of these things. Here, the disjoint union, we have different dimension, but yeah, I should write this here. The dimension is the number of parameters of orbits here. So this is the dimension of the missing g here, z, g, x, reg, mod g plus the dimension of g. So here, with only one element, we add dimension of g, and here we have to add some number of parameters of orbits, the dimension of the orbit space. Okay, so and this leads us to sheets. Here, one thing which is important is that we have this equality of dimension, and we look at under first projection, we have fibers with the same dimension. So the sheets, by definition, you look at all the this is valid, the definition which is valid for over any representation. You look at the dimension of the orbits for any element, and the sheets are only the irreducible components of these sets. And if you define CS of G for S a sheet as the set of pairs in the commuting variety with first element in this sheet, this is irreducible of dimension of G plus dimension of S mod G. And this dimension of S of G mod G is just the dimension of S minus this small m, the dimension of the orbits. So if you understand sheets, then hopefully you can understand better the commuting variety, and that's why I first looked at it in my PhD thesis. Okay, and the rest of this section is dedicated to the study of these sheets in the Lie algebra case and in the symmetric Lie algebra case. So first, the Lie algebra case, and there are some decomposition classes, as I said. Here you consider the Jordan decomposition of an element, and you will look at all the elements with similar Jordan decomposition up to the action by G. So what does it mean? If S is diagonalizable and N is nilpotent, let's say in GLN, but it works over any field, just to set up the ID. So here S has eigenvalues, and what you do is you allow lambda mu to vary. So this is this part, and what I've drawn in blocks here and what appear here is the levy. This is a product of GLN in the GLN case. So this is what is here. And then you add a nilpotent orbit, and this nilpotent orbit is encoded by Jordan blocks. So this is this O here and this N here. And the number of parameters of this decomposition class is dimension of G of X mod G is just the dimension of this centralizer. So it's kind of easy to compute whenever you have L and O. So yes, this idea of fixing L and O, so you choose a levy, so this is blocks on the diagonal, you choose an nilpotent orbit, here O, which is encoded in GLN by Jordan blocks. One important thing is that we have only finitely many such choice up to conjugation of levy and orbit. Yeah, something missing here is that O is a L nilpotent orbit in this levy, where L is a group associated to small l. Okay, so now some classical results about decomposition classes. Decomposition classes are finitely many, and they are very nice varieties since they are smooth, they are irreducible, and they are also locally closed. And sheets are parameterized by Jordan classes, or stratified by Jordan classes. So they are union. I said Jordan classes, this is the same as decomposition classes. We can write any sheet as union of decomposition classes. There are finitely many, so there is one class which is dense in each sheet. There are also some nilpotent. Well, when you have a nilpotent orbit here, it's just a G orbit. We'll come back to it later. And we have, this is the work of Bulois and Kraft. We have something combinatorial to encode those inclusions. We have a decomposition class which is included in the closure or the regular closure of another decomposition class if and only if there is some induction of nilpotent orbit here. So here again I need some notation. So L1 and L2 are two levy, O1 and N2 are two nilpotent orbit, and I assume that L2 is included in L1. All of this is up to the G conjugacy, and this is the parabolic induction of nilpotent orbits, and it works for Lie algebras. So you can very much describe those sheets in terms of some combinatorial results here on those pairs levy nilpotent orbit. Some other results, which are due to Imhoff and Petersen. Imhoff got the smoothness of the sheets in the classical types, and Petersen got one singular example in G2. So sheets are a bit less nicer than decomposition class. They are not automatically smooth. And one important consequence of this is that sheets are classified by pairs of constituted by a levy and nilpotent orbits, which encode in fact the dense decomposition class in S, and the dense Jordan classes in S are when O is rigid in L. And what does it mean? It means that for all L2 inside L, for all orbit O2, so this is an L2 orbit, we don't have the induction of from L2 to L1 of O2 is different from O. So those are the nilpotent orbits which are not induced from any other orbits in smaller levies. In this case, we call them rigid. It's possible to classify rigid orbits, and we have a classification of sheets by this mean. Okay, so the idea next is to tell you what happens in the symmetric Lie algebra setting where I worked. So first, some known results. In the symmetric Lie algebra setting, you look at the action of G0 on G1. So you are interested in element of G1. There still is a decomposition, Jordan decomposition. You can look at pretty much the same object, just you ask for the element to lie in G1 and you take the action by G0. So this is what I have written, the JG0 of X. Again, Jordan decomposition classes are finitely many. They are locally closed, irreducible, and smooth. You can find it in some works by Tovel and Yu. Also, I learned from Michael Le Barbier that he had a proof for the fact that sheets are union of decomposition classes, but we had no notion of induction here. So what appears in gray here was not known. we can deduce the smoothness of the sheets in the classical types from the smoothness of sheets in the classical types for the Lie algebras. So I've written this here. This is not very important for the following, and sheets are classified by some pairs, but it's kind of hard with this to say exactly what are those pairs of a Levy and a nilpotent orbit. Maybe one precision here. L here is still a Levy in G, and O is a Nel0 orbit in L1. So the Levy has to satisfy something. It has to be the centralizer of a nilpotent of a semisimple element in G1. And what I want to present are our results with Pascal-Hiver. And those results states what was missing here. So we have a notion of induction, which is not parabolic induction of nilpotent orbits, but what we have called slice induction. Also, we looked at examples in G2, and there is still a singular example. But the main thing is that we can recover this fact. The fact that any sheet is a union of decomposition class. Thanks to this property, we can describe precisely what happens, what is the closure of a decomposition class. And this is valid over any algebraic closed field of characteristic 0, and I'm pretty sure that things can be written in more general setting even, while the proof of Le Barbier was only valid over C, really C here, with analytic methods. And a nice consequence is that we can now write this thing. Sheets are classified by pairs with a Levy, a nilpotent orbit, with the nilpotent orbit being rigid in O, with the same definition of rigidity that is not being induced by some smaller thing. And what I want to present you is what does this induction thing looks like. So I've written this here. Once again, the idea here is that L1 is just G. Things are written more easily in this setting. And so this is our orbit. And our orbit is just a decomposition class here. And so this orbit, saying that this orbit lies in the regular closure of this decomposition class, this is what we rewrite as an induction step. And in this setting, we say that we have an induction whenever the decomposition class here intersects some affine slice. So here U is included in V. It's even not that it's linear. It's not affine. What is affine is E plus U. So we have an affine slice. Here I should say that U is just G of F, where E is embedded in an SL2 triple EHF. So this is very much like a constant slice when E is regular. And there are also lots of works of Slodowee, Catilo, Imhoff, which uses this setting for sheets or for different objects. But here, a whole inclusion of a variety is encoded by the fact that we can find one element of this set here in some slice. So this has some important consequence that which I will list. This is some work in progress. I have an algorithm to find rigid orbits. The idea is that you can look at the set of elements with dimension of orbits less or equal to m, and you look at equations for this. For example, it's encoded by some minors of some matrices. And once you have the equation, you can look at equations of the intersection with E plus U. And so you can compute the precise equation, and if the vanishing locus is precisely the element E here, then you have a rigid orbit. What I should have precised here, the interest of looking at such an affine slice here is that the G0 orbit of E intersect this slice only at E. So you mod out all the orbit part and you have something which is of very much smaller dimension, and so equations, which can be quite nasty at the level of the whole variety, are much easier at this level. So this is an effective algorithm. I've already computed it in all the exceptional case up to E8. It works. We can also opt for an algorithm for induction, and for this you need the equation of let's say GL2O2. If you have the equations for this variety, then you can do the same thing and look whenever you have okay, and then the question is does E lies in this set of equation, in the vanishing locus of this set of equation. It seems to be doable, but it requires yet too much computer time. It's not really effective yet. Basically, the idea is that you start with the set of equations for the set of elements which have dimension of orbits less or equal than m, and then you force the semisimple element to satisfy some invariant theory equalities. You're saying that the semisimple part lies in the center of some levy as a traduction of via some equation in the quotients. But yet it's not really effective. And also you can look at the geometry of sheets. The idea is that you have G times E plus U, say, intersected with some sheet S, and you look at the orbit map. So this goes to S. This map is smooth. So E plus U intersected with S has the same up to smooth equivalence, basically the same types of singularity as the sheet itself. And I've used it to look for singular sheets in the exceptional cases, and it turns out that there are singular sheets in some singular sheets in each exceptional case. And the hope can be also that if you know the geometry of the sheet, maybe you can understand better the geometry of the commuting variety, but I have no result in this direction yet. So this is all I wanted to say about sheets, and then I come to the Hilbert scheme. So what is the Hilbert scheme? The Hilbert scheme is defined via a representable functor. Applied to a scheme S, this is the set of subschemes of the plane A2 times S, where we want that Z over S is flat surjective of degree n. So when you have a representable functor, what you want to do is to understand it first at the level of points and what are the C points. So if you take S, which is spec of C, then you get that this Hilbert scheme is just the set of subscheme of A2 with the length of the subscheme Z is equal to n. So here a subscheme of A2, this means that Z is the spec of Cxy, which is made out by an ideal, and this must be of dimension n. So those are zero-dimensional schemes. For instance, if you take n reduced points in the plane, this is an element of the Hilbert scheme. And one example I want to describe is this one. if you take this set of equations, so you take x squared, y squared, xy, so basically you have a fat point here, and you add one more equation, so you ask for the scheme to lie on a line here with equation ax plus by is equal to 0. What you get is something which is supported in 0. There is only one point in this subscheme which is supported at 0, and it remembers the direction of this affine line here. Okay, and what we can say then is that Hilb0 of A2, here we take n is equal to 2. This 0 here is just to say that we look at schemes which are supported at the point 0. This is only P1, just to give an example. And those are exactly the set of such schemes which remember only a direction here. In general, we are interested in many different types of Hilbert scheme. This is a kind of fundamental object in algebraic geometry. And what I will present will be on those different Hilbert schemes. So you have the Hilbert scheme, classical Hilbert scheme that I just presented. You have the local Hilbert scheme, so supported at 0. And you have those nested Hilbert scheme, which are written here on the right. So what is the nested Hilbert scheme? You ask for some inclusion of some subschemes where Z1 here is of length N1 and here of length Nk. So given some N1, Nk with these inequalities, you can ask for all the subschemes with those given lengths. So this is what is called the nested Hilbert scheme. And there is a relation between the Hilbert scheme and the commuting varieties. So here the classical Hilbert scheme is linked with the commuting varieties of matrices. When you ask for local Hilbert scheme supported at 0, you get nilpotent elements. If you have nested Hilbert scheme, you get the commuting variety of a parabolic. So here you can add nilpotent. First, this was done by Nakajima on the classical Hilbert scheme, and it has been used in several settings. And what we've done with Laurent Evin was this setting of a parabolics and nested Hilbert schemes. That was only 20% of our paper, but that's the most important part, I think. What is the connection? So if you start with a subscheme, so if you have Z, which is included in A2, so Z is just spec of kxy mod I. This is of dimension n, and you can act by multiplication by x and by y. Here you can see these elements as endomorphism of this space, which is a n-dimensional space, and those two elements commute because this is only commutative algebra at this level. So you get an element in the commuting variety. What is the precise link? The precise link is the following. The Hilbert scheme is isomorphic to a quotient of a variety which is related to the commuting variety. Let's define this for GLN, say. So this is the set of triplets x, y, and some v, where you ask xy to lie in the commuting variety and v to lie in Cn. You have the action of GLN on Cn, and you ask that v is cyclic for xy. The existence of a cyclic element for elements arising from a point of the Hilbert schemes is that 1 is a cyclic element for the action of x and y. And then you can look also at the projection on the commuting variety, and this gives you this. Okay. So the result is that the Hilbert scheme is just the quotient of this variety by G. And you have analog for any of the Hilbert scheme mentioned here. And said theoretically, we can write things in terms of the commuting variety itself. Yes, what is nice in this setting is that the G action is free, so the quotient is very nice. Said theoretically, we have a bijection between the irreducible component of the Hilbert scheme, which are of dimension m, and the dimension of the commuting variety with here something, some term in addition. We should note that this is included in the set of irreducible components of the commuting variety itself. Okay, so this is for the link between the Hilbert scheme and the commuting variety. So if I sum up things a bit, you have here Hilbert 0. So let's look at the nested Hilbert scheme at 0. It's linked with the nilpotent commuting variety of P, and it is linked with the same ideas as before to the sheets in the nilpotent part of the parabolic. So if you can understand the sheets here, then you have information on those two varieties. One special case is if there is finite number of p orbits in this nilpotent set, then this commuting variety is of dimension p minus 1. Dimension of p minus 1. Okay, and the result we got with Magdalena Bus was to classify all the parabolics with this property. So this is kind of nasty if we look at what it looks like. It's not really nice. So this is not really n1, n2, nk, but this is something which is similar, and we have classified all the sizes of the parabolics for which we have infinite number of orbits and for which we have a finite number of orbits. One interesting case is that when you have only two blocks for the parabolic, when each block is of dimension at least 6, then you get infinite families of orbits. Okay, so we got this classification after a lot of works. In these cases, as I said, those are the cases where the commuting variety, the nilpotent commuting variety, is as small as possible, and where the Hilbert scheme is also of dimension as small as possible. You don't have big components which arise. And I spoke about the maximal parabolic case. Maximal here means that P is just something like this, and N1 is the size of this first block, and I ask that each block is of size at least 6, then the dimension goes one step up. You have one more dimension here and one more dimension for the Hilbert scheme. So there you start having troubles, you start having big components in the commuting variety, and things get worse when you increase the size of the parabolic. And also we got some results for the commuting variety itself, not the nilpotent one, but the commuting variety. And it might be reducible even if P is maximal. So that was some new example of reducible commuting varieties. Okay, do I have time to go in the proof?
You started at 2, but you can take 5 minutes.
Oh, okay, so then I will be brief. The idea is that you can reduce the study of nilpotent orbits via the representation of some quivers. Then such quiver, you have some covering theory, and you can relate it to some quiver where all the loops are not loops, but some vertical arrows here. Each loops is a composition of several vertical arrows, and this is allowed, especially since you look at elements which are nilpotent. Here beta S is the nilpotent orbit, and here the dimension is n1, n2 up to nk. So here you have a nilpotent orbit in GLN-K. But I have no time to discuss this in more details. You have covering theory, so you are happy because there are lots of results for quivers. You have this BHV list, which lists all the minimal possible cases where for quiver with relation when you have infinite family of representation that arise, and this helps us to find many different infinite families, and with lots of other computation we could show that all the other cases were finite. So that's all, and I want to thank you again.